Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about contactors. They are very important electrically. So let's dive right into it. Why exactly do we have need for this contactor? Well, reality is power ratings of many devices are ludicrous. Basically, most of us are familiar with 1 kilowatt. 2 kilowatts, maybe 5 kilowatt, but you could have an industrial scenario where each motor individually could be 10 kilowatt or even 20 or even 100. Or let's not even go into furnace industry. That puppy is like, I eat megawatts of power. So power ratings in industrial sector or even large building commercial sectors could be huge. I mean, idiotically huge. And many a time, whenever you are dealing with this sort of oomph, flat out, you have to use three-phase power. Flat out, like there is no option there. You have to use three-phase power. And simple switch, the humble switch that thing go like this, tick took, is just single pole. So flat out, it cannot switch a three-pole system safely. And then there is another problem. These switches are not designed for to be robust enough. Meaning, whenever you are dealing with electric motors, you are also dealing with not just the current that it will draw when it's running. It will also deal with inrush current, and that inrush current could be idiotically huge. Same goes with a very huge inductive loads or many appliances have like smoothing capacitors. Many of time they have power factor correction, which literally if you have a lot of them piled up together, it will act like with your substation side of you, it will act like you created a dead shot again for a brief instant, but that brief instant is more than enough to destroy your switch every time you turn it on and off. And normal switch will simply not last long enough. And then we had like this sort. I'm reasonably sure most of you not living in India have not seen something like that, where you have to have handle khatang khatang. We used to do that. It did require a lot of power. Again, it was safety feature. It was designed in such a way that spring force was enough that it either was like on or off. It was never in like in between. So we used to have that. Now again, whenever first time we got three-phase power and first time had three-phase motor, this was the option. But there is a problem with that. It does work. It's a useful thing we used in 1950s, but it does not have remote ability. Meaning, if you are running an industry, a farm, or whatever have you, where you have this sort of motors, a person actually has to go to the switch and turn it on. And the inherent design is not very what you call automatable. Is very manual. It does work, but very manual. So that's why there was a need for something more contact based. Contactor. Now contactor is a literally spring loaded switch. That's all it is. Now design of the switch is rather very ingeniously done, meaning whenever you talk about normal switch, it has the things that are swinging. Now if you know about metallurgy, you know for a fact no amount of spring, no amount of something that is going flexing, basically it will not last. Flat out it will not. Even springs are specifically designed so they flex very little. You do not want a spring that's going this much. Even if it can do that, if you do it long enough, it will fall apart flat out. So you want very little, very little. These are absolute requirements. So a spring loaded switch was designed where the spring had to travel very little. So it's like very not too compressed, not too relaxed. So it can withstand multiple cycles compared to a normal spring, and there is nothing that is flexing, no going twing like this. And an electromagnetic actuator, like what actually turns it on, it's a electromagnetic power, basically coil like this. So what you will have is basically three-phase power. Most of the contactors are generally three-phase. It will go here. Now there is a floating bar that will supposed to connect it, but it will not do it. The moment you turn on the coil, it floating bar again creates a magnetic field that brings this puppy down, and then the plunger makes the contact. Now all these three things are freely independent, and all these three things are designed for high amp ratings, meaning again depending on a requirement it could survive in rush current of 100 amps, 500 amps, or depending on some huge system, megawatts of in rush current. And that's how you get the contact. But be mindful, this is a coiled system, meaning it does have active draw power, meaning all the switches that we utilize, they are latching kind of system, meaning you turn it on, that's it, you don't think too much about it. This does require power to stay on, basically. And majority, almost all of them, primary contactors are generally always normally open, meaning you have to put power in order to close it. Now again, it could have some auxiliary ports that are designed invert of that for diagnostic purposes, or some diagnostic lights, but generally most of them are designed in this similar way, where the turning it on means you will close the contacts. Needs current to operate. Now the primary reason why we go for this is like they can survive millions of cycles. What does that mean? That simply means if you have a MCB, you may think, hey, I have a MCB, it's designed to break ludicrously large amount of inrush current and handle those sort of things. Why don't we just tuk that? Here's the deal, you can do that, it will work, but it will not work for long, because many MCBs that are like very well built, very robust kind of design, they are designed for 10,000 operations. You will go through 10,000 operation very quickly if you are doing it multiple times a day, and you will be like this super expensive device, and it will not even be safe because that spring is not designed to be like, ting tang tung ting tung ting. It's not designed for that. This system, on the other hand, is specifically designed for that. Every aspect, every plunger, every spring, every coil, every insulation, every debouncing system that is put here, all of them are designed for that reason. Whereas like it can work for a very long time. For example, the spring, you may think, let's put a very strong spring. You have a backfire problem, because if you have very hard metal, like going super hard, going twing, it will bounce. Now the moment it bounces back, it will create an arc, and God help you if that arc happens in AC waveform when it's going peakwards, it will literally melt it shut. It has happened to enough people where like, they shall use properly balanced spring. That's why every aspect of this is fine-tuned for millions of operational cycle. That's the prime reason we choose this, because you can try other things also, but like this is one of those things where if you had a properly sized equipment, you will literally be like, yeah, it was installed in 1950, it's still working. There are many like back in the old days, people used to actually replace coils if coil ever got burnt out, but nowadays, like, again, it's cheap enough where just throw the whole thing, but you can still do it. And again, if you are just experimenting and playing with things, you can buy many broken one, which generally will have coil that is like, shorted, and you can replace the coil if you are willing to put in the time. So how do we drive this magical contactor? Well, the coil needs power. However, it's small, but it does need power. So you have to control the power side of it. Now, majority of systems that you will buy generally use AC coil. Consequence of AC coil is that it does have noise to it. Basically, it's a AC sine wave, so it does have to it, the hum. Again, that may not be annoying, but it could be ludicrously annoying if you have hundreds of this. And there are some industrial cases where you could easily have 20, 30, or even more than that. So in those sort of scenarios, that does make an issue. And there is another aspect. It does draw power. It's an active switch. It's not a latching system. It's active. There are some latching designs, but generally people do not prefer them simply because they are not as reliable as this. Basically, this core system can last for 10,000 years, but if you have a physical plastic bridge that you can buy, the flat out the company will tell you, dude, this is only rated for 10,000, because again, flexure structures do not last for very long. So if you want absolute reliability, you will go with coil routes. But problem is it does draw power, and because AC sinusoidal wave is not really good for making electromagnets, somebody figured out, what if we use DC coils? Back in the day, it was very difficult to do simply because where the heck you were going to get, semiconductor was not mature enough. Nowadays, we do have a lot of mature semiconductor industry, and many industry do want contactors to control their stuff, but they do want to control it with low voltage. Now, problem with low voltage is that it does not have enough oomph, but if you have a magnetic coil, DC is perfect for that. So you can have very high power draw relay system. Basically, it's a bigger brother of relay. It can switch very large amount of amp, but you can drive this with 24 volt DC. That's the interesting aspect of it. So if you have, let's say, industrial smart controller that wants to control these things, it does not have to touch hands. Basically, it does not want to even touch any sort of high voltage. It just wants to touch DC voltage. And let's say all the system was in your board was designed for 24 volt. You can just buy relays and contactors that are built for 24 volt. If your system is built for 48 volt, you can just buy contactors that are 48 volt rated, meaning you do not have to switch hands. Basically, you can have a floating system on top of your contactors where it's like everything else is independent. Everything else is just like 48 volts. If you are dealing with like long wirings, you generally have to go to 48 volts. If you are dealing with power over Ethernet, it can also go up to 48 volt. Generally, people do not want to exceed 48 volts simply because it crosses 50 volt, and at 50 volt, it can cross your skin. Meaning, if you are ever touching 48 volt, chances are you will survive. You will not have any issue. 12 volt, super safe. 24, super safe. 48 is like the upper limit. After that, most countries are like, hey, at that point, it's dangerous. 72 volts, yeah, there is a very good chance you're gonna go up. And DC voltage at 72 volt, yeah, you directly go up. So that's why low voltage are generally preferred. So you're only gonna find either 24 volt or 48 volt. 72 volt do exist and they do have some benefits, but it's not desirable simply because the low voltage is not low enough. Yeah, it's low, but like low compared to like 400 volt three-phase system. That's not really low enough. So coil controls allows remote operation, meaning the current draw, basically the amount of watt it consumes, it's very low. So you can remote trigger it either by solid state relay systems. For example, if you want to directly drive it with Raspberry Pi, you can do that, or you can just have a low power switch, which is like toggle switch. You tuk, and the switch will not wear out because the main oomph is withstand by the contactor system. And low power for auxiliary ports are also added nowadays. For example, you will have always the three main things, the main boy, but you will always have a one small one added there that will be normally open or normally closed depending on the manufacturer. Now those are generally for indication lamps, some sort of feedback loop, interlock, those sort of thing. They are not for heavy loads. Basically, your three main system It's designed for like main oomph, like your main induction motor inrush current. But that side one, that will be like very normal basic switch. Now you're like, why do you want that? Again, it's up to you. You can design auxiliary schemes for that. For example, you have the 3 main system. How do you know which contactor is working? Again, you will have light which will show both state, on or off. Now you're like, why the heck you want a light that shows it's off? Well, that means the box power is working, meaning if you have an industrial box, power is going to the box. Motor is off, if it's showing off, and then motor is off, that's awesome. If the light is not off, motor is still working, that means something went wrong, super wrong. Like you could have some short circuit somewhere else. Or like again, if you want to work on it, you have to turn off the main system, and you will know, hey dude, that red light that shows off, it's not on. That simply means the power is not there. So you will not accidentally open it, hey, motor is off, so I'm opening the main board. You do not want to do that. So there are many actual legal reasons where you have to have systems where main contactor is like, piggybacked in a such a way where you can have auxiliary units on top of it. It will allow other things added. For example, you can even have some systems where you have dampening resistors that really handles inrush current. That will allow your system to last much longer compared to without having dampening resistors. So that's how auxiliary ports are there. So you're like contactor on, contactor off, contactor A online, contactor B online, and it can even deal with PID control. And then it will have PID control will literally work on the same voltage as like it's designed for 48 volt PID controllers or 24 volt system. It will be completely floating without touching the main system. That's why driving, it's up to you. You can do amazing thing with this, but you have to drive it. Now, logic is the whole interesting part of it. It's not just a dumb switch. You can do so many things because you can add so many things to it. So based on that, you can just have a normal switch where it's just like, hey, I'm turning on a big, let's say, submerged water pump. It's just a switch for me. That's okay. That's completely fine. But if you want to do more with it, you can have auxiliary port. Like then you can go YOLO on it. Then this sort of auxiliary port. That's what I'm saying. Like the big fat cable, those are motor cable. This small low voltage cable, they are designed for PID loops. Or in some scenarios, you can have like them. Still, it could be running on the AC, but it will be very low amp, like a bulbs that are like you're showing, hey, the contactor A is working, contactor B is working, contactor C is working, contactor C is closed. Depending on your design, you can set whatever the hell you want to. It's up to you. And sometimes you will have basically timer. Sometimes you will have interlocking circuit, meaning if A is on, B will not come on no matter what happens, like lighting circuits, things of that nature. It's completely up to you. You add auxiliary port to these puppies and you go YOLO on it. Normally open, normally closed, both are available. Meaning if you have a scenario where you want to always use normally open, you can buy it. You want normally closed, you can buy it. That's up to you. Latching systems are already used. Like generally you will always see latching system because industry does not like the idea of a switch that can get stuck. Meaning if you have a switch, it should not be in a position where it can get stuck in one position, either off, either on. It should not get stuck. So generally they like toggle switches. You just turn it on, not toggle as in a push switch. That's why you will see like industrial big yellow boxes with like giant red and green button. Those are latching circuits, and the power on those switches are very low, and if you press it for too long, it will stop working. It's designed in such a way. So it's almost like how a railway locomotive, they have a switch there, and that switch is double latched, meaning if you press it on for too long, it will apply emergency brake. If you do not press it for too long, it will apply emergency brake. Meaning there is like, it depending on the design, it could have like 20-minute alerts, and it has a randomizer after 15 minutes. So first 15 minutes is like, okay, I'm cool. Then it randomly beeps an alarm, and then the driver has to tank it. If driver puts a brick, which older design used to be, again, many accidents have happened. So we are like, no, it has to be double latch, meaning you turn it on, then you have to turn it off also. If you don't, the train applies emergency brake. So latching systems are there. Timer based systems are very popular for lighting circuitries, and then you have whole control system up to you. It's up to you. You can go YOLO on it. From a basic motor controllers to advanced robotic systems can be done with this. Conveyor belt system can be done with this. It's up to you. Because of the auxiliary port, you can go YOLO on it. So what are the uses of it? Well, everywhere. Everywhere where you're dealing with power, unless you go to substation, one step below substation, you will find these things. Everywhere you will find this sort of big building, you will find contactors. Big motors, you will find contactors. And many times whenever you are dealing with a large power induction motor, people use what we call Y delta starter, meaning the motor will start spinning on Y configuration. It generally will have very low inrush compared to delta. It will still have inrush, but compared to delta, it will have low inrush. And once the motor has spinning momentum, again, depending on the load on it, programmer will program like, hey, stay in Y configuration for 5 seconds, or stay in Y configuration for 15 seconds. If let's say it is very geared down, it will take time to spool up. It will wait for that, then it switch to delta, which is far more efficient. You can do that. And when you come to EV industry, everything runs on contactors, everything. Whenever you figure out, like when you go into an EV car, you put your key, you turn it on, there is a click. katang, there is a like very solid click. You can figure it out. Even if you have car with sound dampening, you'll figure out something clicked. What the heck clicked? This thing. This is from TDK, designed for like 400 volt DC systems to 600 volt DC system, and it can safely break upwards of 500 amps. Now, AC is kind of forgiving when you want to break the circuit, because if you have break circuit like this, you are breaking it. The worst case time scenario would be when it's like at peak voltage. Now again, the peak, you have the most amount of arc, but here's the deal. Even though you are sustaining the arc, the voltage is dropping, it's going to zero. It's gonna phase out the moment it goes to zero. So self-extinguishing. But when you are dealing with DC circuit, it will not, there is no self-extinguishing. That's why like people dealing with solar, they hate this part of it. That even if you have like very low voltage, let's say 48 volts, so it's completely safe. Even if you touch it, safe. Here's the, if you arc it, that arc is not self-extinguishing. It can literally keep burning. It can melt through metal. Again, it's an arc furnace at that point in time. So DC system, especially in cars, that are going to like 400 volts, or some people are trying to put 600 volts. These contactors are becoming very tedious, very complex to design. Like you have to literally rely on distance in order to stop it. In some scenarios, some of them utilize vacuum systems. And then also it's not very, because in this system, this gray block you are seeing, that's ceramic, because the heat generated in this area is so hot, nothing will last that long. And not to mention this, these things require the most amount of care to it, because what happens in an accident, this puppy disconnects everything. What happens when you turn your key and walk away, this disconnects. Everything relies on this. If this does not work, your car is not safe. You could literally have 400 volt touching something, and 400 volt, even minor arcs would be more than enough to set your building on fire. So EV industry needs this. And whenever you talk about AC level 2 charging, and it's like this big box, or like what magic, nah, it's just a contactor. It's just a contactor which just have enough smarts in that, so it can detect, hey, all three phases are consuming power equally, all voltages are in the same range, amps in the same range, and it does tell to the basically car, hey bro, 5 amps per channel. That's it. That's all it tells to your car. It's like 5 amps. Car is like, no, I want 10. It's like, no bro, 5. That's it, the lowest one basically. And if you have like big industrial, is like 22 kilowatt rated, is like I can support 10 amps. It's like car is like, bro, I only take 5. Oh, no problem, it's just a plug at that point in time. So all it does is just disconnect it. That's how AC level 2 charging works. So fundamentally speaking, entirety of EV industry relies on very top quality contactors. If they don't have it, it won't. And like you will figure, you will be surprised how much engineering goes into electrically make sure this thing don't fry. They have like a dampening resistor. Like there is a whole circuit that just dampens this arc. Because without that, yeah, this contactors, even the company making it's like, yeah, bro, you want to use it raw? How many times? Oh, every day? Yeah, no, bro. It's like 3-4 months, this will be cooked. So they need a dampening circuit for it. And industrial control of power systems, again, that's up to you. That's, you can build surprisingly amazing. That's how we used to do things from 1950 to now on. Even now, all the only difference would be there will be a lot of auxiliary port, lot of cables that are driving the PIDC loop. Other than that, nothing else. So there's a very serious use of it. If you want to understand power electronics, you have to understand contactors, and you can build like whole car. People have built like literal car lifts that are just using contactors. No microcontroller, no fancy thing, just contactors. They're going up, going down, stopping, everything. So they are amazing devices. Like you would not think how amazing they are, but they are very amazing. So this was my presentation on contactors. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.